Welcome back after the short break. So, what we are talking about different realizations and different variants of differential amplifier, and primarily in our next discussion we will be talking about this circuit and this circuit as a representing basic structure. Now, if you want to see the basic working principle of this circuit, particularly this circuit or this circuit, we need to convert this circuit into one of its equivalent. So, let us see in the next slide what equivalent circuit we are talking about. So, here this is the basic differential amplifier using BJT, and here we do have tail resistor called RT. So, this kind of circuit so far we have not analyzed, but at least we have analyzed something similar, particularly if I consider only half of this circuit, something like this. And if we feed a signal at the base and if you observe the corresponding output at the collector, we know that this is CE kind of circuit. So, we also have seen that the emitter node need not be connected to ground, even if it is connected through a resistor, still we call this is CE amplifier, considering this is input and this is the output, right. So, since we know the analysis of this circuit, I think it is better we go inside this circuit, rather convert this circuit in this kind of form and then try to analyze the circuit. In fact, in case if we are observing the output at this node and if it is remaining as input, even though we do have say resistor connected here, and if I call this is our new output, then we call this is common collector circuit. So, even in this case also it is better we convert the differential amplifier in terms of this kind of structure. Now, in this original structure, this RT, it is connected to Q1 and Q2 together, but we also know that Q1 and Q2 and then RC1 and RC2, they are respectively identical. So, if we split this circuit, if we modify this circuit in some way so that we can have two identical halves, probably then our analysis it will be simpler. So, instead of using only one RT, let me consider that two RTs are parallelly connected to realize this RT. So, we are keeping this node connected. So, this circuit, as long as this is connected, this circuit and this circuit, they are same. So, in our subsequent analysis, instead of really going into this circuit, we will be talking about the analysis of this circuit for simplicity. Namely, if I split the circuit into two identical half, then probably if we feed a signal at the base, then we can see what kind of signal we do expect at this terminal and this terminal. So, same thing for the MOSFET version. Instead of analyzing this circuit directly, let us split this resistor into two identical parts, each one of them is 2 RT, so that we can prepare this circuit such that whenever it requires we can split the circuit into two identical halves, and that is the corresponding circuit. So, in our next analysis, instead of using this circuit and this circuit, rather we will be considering this modified circuit. I should not say modified, but it is structurally it is different, but they are actually same circuit. So, in the next item what we have is analysis of this circuit, rather this circuit, and try to see its operation, basic operation. So, here is the circuit. Before we really go into the analysis, what we have done here it is we have simply disconnected these two terminal. Then naturally, this circuit and this circuit, they are not same. So, of course, this is different, but then depending on the situation probably we can make say left half and right half separate. Now, while we will be applying the signal at the input like this, namely at this point we do have one signal called V in 1, which is riding on a DC voltage called V in C in capital, that means DC, and then the signal we are feeding here it is V in 2, which is also on the same DC voltage V in C. So, same thing in the modified circuit, here also we consider that we are applying signal here V in 1 and V in 2, and both of them are on the same DC voltage called V in C in capital. Right. So, by doing this, what we can say that whenever we are applying a signal here and here, probably since we are familiar with this circuit and of course, this circuit, then we can see what kind of signal we are getting at this point and this point, and also we can analyze the circuit to really understand that what kind of DC voltage we require here for proper operation of this transistor and the circuit. So, let we consider this half. So, one of this half and try to understand that what kind of signal we do get. In fact, we already have seen this kind of circuit before, but it is more like a recapitulating whatever we already know it. Okay. So, let me redraw again, clear and redraw the circuit. Let you consider we are applying a signal here on a meaningful DC voltage, and when we say meaningful DC voltage, this DC voltage should be sufficiently high, so that transistor 1 it is remaining in active region of operation. Now, for a meaningful collector current, we need this voltage, DC voltage should be at least 0.6 with respect to this ground. So, we are assuming that this V in C it is higher than VBE on say 0.6 volt, and then based on that, based on how much this voltage it is higher, the corresponding emitter voltage it will be higher than the ground, and then it will be having a current flow, and let me call this current flow it is I t by 2. Okay. Later I will discuss about why we consider I t by 2, but let you consider this is whatever the current it is flowing, this is I t by 2, that is also setting the corresponding collector current. You can approximate that this I c collector current is equal to I t by 2. So, that sets the proper region of operation of transistor 1, and hence we can probably calculate its corresponding GM and then R pi and then R naught based on whatever the condition you are putting. Now, if you see this circuit and if I feed the signal at the base, then at the collector what you are observing this VO2, and since this emitter node it is degenerated by this resistor, we know that the signal will be getting here say VO2 equals to, if I call this is V in 1. So, VO2 it will be minus GM of this transistor called GM1 multiplied by RC1 divided by 1 plus GM1 into 2 times RT. In fact, this expression we obtain by considering something called common emitter amplifier, where emitter it is getting degenerated by 2 RT, right. And you may approximate that this is equal to minus GM1 RC1 divided by GM1 2 times RT, or further to that you simply remove this GM. So, we do have essentially minus RC1 divided by 2 RT. So, that is the signal, that kind of signal we are expecting. Sorry, I forgot to write the signal part. This is multiplied by V in 1 multiplied by V in 1. So, we can say that VO2 divided by V in 1 equals to RC divided by 2 RT. Okay. So, depending on this ratio, we are expecting some signal here. So, if I observe the signal here, say it is having a DC voltage defined by V in C, and this is a corresponding signal. So, this is capital V small in 1, and this part is the signal here. So, the corresponding output what we get here, it is having its own DC level. Now, of course, this DC level it can be obtained by considering VCC minus this IR drop across this resistance due to this quiescent current IC flowing through it. So, this voltage we know how to get it, and on top of this one we do have this signal. Just now we have derived its expression. It is having a minus sign, and probably it is having some amplified version, and this amplification with respect to this input, it depends on this ratio, right. So, it may be amplification or attenuation. Of course, it depends on the relative value of RC, RC1 and then 2 times of RT. Now, if I consider the other node at this node, and if I call this is the emitter signal at transistor 1 called say VE1. So, now the circuit it is basically it is working as common collector circuit or something called emitter follower. What does it mean is that the signal we are expecting here, it will be almost same as whatever the signal you do have. So, you may approximate this equal to V in 1, and it is in the same phase. In fact, it's supposed to be slightly less than V in 1, because we do have some signal between base to emitter, and that is how we are getting the current here. It is having signal, and hence we obtain this signal, but the signal here at the emitter node, at this node V1, it is very close to this signal, and they are in phase. Now, if you also look into the emitter terminal, we can find its corresponding resistance. In fact, if you look into its emitter terminal, what we do expect that it is having a signal, and this signal it is VE 1, which we claim that it is very close to V in 1, and then it is having its own Thevenin equivalent resistance, and that Thevenin equivalent resistance we know this is common collector stage. So, that is R pi in parallel with 1 by G m 1, and then it is connected to 2 R T. So, that is what we see here at this point, and you can probably approximate that this 1 by G m it is much smaller than R pi 1. So, you may consider approximately this resistance is equal to 1 by G m 1, and then this resistance is typically it is much higher than 1 by G m. So, you can further approximate that this is equal to V E 1, and this resistance it is 1 by G m 1. So, I should say this kind of Thevenin equivalent signal source we can see here, right. Now, so now let me again summarize what we said here. It is that if we feed a signal at this point called V in 1 on top of a meaningful DC voltage, let you call V in C, so that this meaningful voltage it is ensuring that this transistor it is in active region of operation. Then the signal we observe at the output terminal, it is V in 1 multiplied by R C 1 divided by 2 times of R T. That is because of the circuit it is working as common emitter with emitter degenerator. Of course, we do have a minus sign here, there will be phase shift. On the other hand, if you look at the emitter terminal, what we can get that if I call this V E 1, this is the signal. Of course, it is having a DC voltage, but signal wise V E 1 it is approximately equal to V in 1 without any phase shift, and also its resistance, Thevenin equivalent resistance, it is very close to 1 by G m 1. So, looking into the emitter node of transistor 1, what we can say here, it is a voltage signal source having a strength of V E 1, which is very close to V in 1, and then the corresponding resistance of G m 1. Now, if I apply say signal here called V in 2 on the same DC voltage level, Okay. This is very important that V in C it is also coming here. So, this voltage and this voltage they are same, and then we do have the signal here. So, now if I analyze the right half, the signal will be getting at this point, it is minus V in 2 R C 2 divided by 2 R t. And in the same way as we have discussed for the left half, if I look into its emitter, so here also you will be seeing that a signal source called V E 2 and having a Thevenin equivalent resistance which is 1 by G M 2. Okay. Now, the moment we are keeping these two are disconnected, then we do have the signal here. Now, let us see what happens for two cases, namely if I say that the circuit it is stimulus in differential mode of operation, namely V in 1 and V in 2, they are identical in terms of magnitude, but they do have opposite phase. So, then what happens? So, if I assume that this is equal to plus V in d by 2, and then this if I consider equals to minus V in d by 2. Okay. So, this is one case. So, we consider that both the circuits we are preparing in such a way, so that the stimulus it is perfectly in differential form, which means that this signal, so this part it is minus V in d by 2. So, as a result this part it becomes minus minus is getting plus. So, we do have V in d by 2 and then R C 2 divided by 2 R t. On the other hand, the corresponding output here at this point, we do have a minus sign here, we do have a plus sign here. So, so here to here we do have minus. So, minus minus it is getting plus, and here we do have plus and this is minus. So, this is minus V in d by 2 into R C 1 divided by 2 R t. Now, if I assume that this R C and this R C they are same, so we can say that the signal here and the signal here they are identical in terms of magnitude, but they do have opposite phase. Now, still it is okay. So, if I try to plot these two signals, namely V O 2 and V O 1. So, what we are getting it is say V O 1, if I plot V O 1 in blue color, something like this, and so this is V O 1 and then V O 2 in red color, which is similar, or I should say amplitude wise it is identical, but it is having opposite phase. So, this is V O 2 and the difference of course, if I say that V O 1 minus V O 2. So, that is essentially coming as 2 times of this amplitude. So, this is I should say now V O differential. On the other hand, if you see the signal at the emitter at this point. Let me sketch the two signals at the emitter. We do have signal at the emitter which is in phase with the red color. Of course, I am considering differential input, it is in this form. So, this is the signal, and of course, this signal here it is this signal it is in opposite phase. So, this signal it is V in 2, and this signal on the other hand it is V in 1. So, the differential signal we are applying here, it is the shaded part, and the corresponding output here we are getting, which is the differential output. Now, what you are talking about the emitter signal at this point, and if you see that this is almost equal to V in 1. So, we are expecting that V E 1 it will be like this, and the V E 2 it is following V in 2, magnitude wise it is same. Now, it is a very interesting thing it is going to happen is that to get this circuit same as this circuit, I need to make a connection here. So, from here to here I need to connect. The moment you will be connecting these two nodes together, which is having completely identical signal with opposite phase. So, this signal and this signal they cancels each other, and it is making it 0, primarily because their corresponding Thevenin equivalent resistance they are equal. So, the moment we make these two signals are getting shorted, so that makes this node and this node a single node, and making the corresponding output equals to 0. And hence, we are expecting the signal at this point it will be 0. Now, all of a sudden if we do this operation, all of a sudden what we are expecting that the signal at this node it will get amplified. Why? That is because this node earlier it was having a signal because of this emitter degenerator of 2RT, but because of the connection of the other half which is having identical signal, but the signal having in opposite phase, making this voltage it is signal wise it is 0. So, I can say that after making this connection, this node becomes AC ground, or I should say this is virtual ground, which means that this RE it is getting completely shunted by this AC ground. So, then this 2 RT is not having any meaning. In fact, if this is if we are saying that by some means we are making it ground, whether by a bypass capacitor or this kind of arrangement, then this circuit it becomes simply CE amplifier without having any degenerator. So, as a result, this gain instead of RC 1 by 2 RT, it becomes GM 1 into RC 1, and of course, this is much higher than RC 1 divided by 2 RT. So, the consequence of this modification, whenever we are making this connection, the red signal, the signal at VO2, it just gets amplified like this with a very big amplitude. In fact, same thing it is happening for this also, because now this node it is becoming AC ground, So, the gain of this circuit, it is instead of RC2 divided by 2RT, this gain it becomes GM2 multiplied by RC2. So, the corresponding output it will be V in D by 2 multiplied by GM2 into RC2. So, this blue color it got extended like this, and it is also having very big amplitude, and the corresponding output, the net output, the differential output obviously, which is the difference of this extended blue color and this yellow color, golden color. So, the corresponding output it got amplified like this. So, in summary I should say that in case if we are making this connection to get this actual signal, actual circuit or equivalence of that actual circuit, and if we stimulate the signal, the circuit with perfectly differential kind of signal, namely V in D by 2 with plus sign as V in 1 and minus V in D by 2 with at say the other terminal for V in 2, then the signal coming at this point, it is minus V in D by 2 into GM into RC1, and the signal here it is plus V in D by 2 multiplied by GM into RC2, and this node it is becoming ground. So, if I see the corresponding output here, differential output, now if I take difference of this and this, where if I take this as positive side and this as negative side, then the corresponding VOD it becomes, which is defined as VO1 minus VO2, it becomes GM into RC, assuming that this GM and this GM they are same. So, GM1 equal to GM2 is equal to GM, same thing RC1 and RC2 they are equal and they are RC, this multiplied by V in D by 2. So, this is what we do get as differential gain, which means that if I take the this 2 it is getting cancelled, because we do have half signal here and another half signal we do have. Now, if I take the ratio of the differential output divided by this this V in D, then the corresponding gain of the circuit it is GM into RC. So, what we are getting here it is VOD divided by V in D equals to GM into RC. In fact, this gain it is same as common emitter amplifier gain. Of course, the minus sign is not here, because we have exchanged this terminal for VO1 on VO2. Otherwise, magnitude wise gain of CE amplifier and this circuit it is same. So, I should say that differential mode gain AD is equal to same as a gain of a CE amplifier constructed by only one half of it, right. Now, next thing is that how this circuit works for common mode, right. So, let us see for common mode operation. Again coming back to the same circuit, we are applying say V in 1 here and V in 2 here. So, V in 1, however, of course, both of them with a DC voltage, V in C in capital, V in C, and however, in this case we consider signal here equals to V in C, and also the signal here it is V in C, which means that it is a stimulus in perfectly in common mode operation. In other words, we are assuming that differential input V in D equals to 0. So, with this operation, before we make this connection, again we can analyze the circuit, and then we can see that the signal coming at this node, it is minus V in C multiplied by R C 1 divided by 2 R T. So, likewise at this point this signal it is minus V in C into R C 2 divided by 2 R T. Now, both this signal and this signal, they are identical, but of course, they do have a different magnitude, and the signal coming at this point. So, signal coming at this point, it is same as the V in 1, and its impedance it is 1 by G m. So, we can say that the signal will be getting at the emitter of Q 1 called say V 1, which is equal to very close to V in C, and it is having a Thevenin equivalent resistance of 1 by G m 1. On the other hand, if you consider the other side, this side emitter node of transistor 2. So, here also you will be having the signal V E 2 that is very close to V in C, and the Thevenin equivalent resistance it is 1 by G m 2. Now, if I see here, both this signal and this signal they are same. So, even if I make this connection, then there will not be any change, because both the signals are same. So, even if I make this connection, the signal coming here it will be this or this, whatever you say, which is V in C. So, even after making this change or making this connection, there is no change of the signal here and here. As a result, these two signals are also remaining same. Now, if I say that individual signal, this signal and this signal, they are identical. So, if I take the average called V O C, let me use different color, it is not so visible. So, V O C equals to V O 1 plus V O 2 by 2, which is same as individual one, namely minus V in C by 2 R T into R C, assuming R C 1 and R C 2 they are same. And from this one we can say that V O C divided by V in C, which is equal to minus R C divided by 2 R T. But this is the definition of the common mode gain. So, we can say that the common mode gain of the circuit it is primarily depends on R C and R T, right. So, by making this two modes of operation, we obtain these two parameters, So, the summary of that, what we say that once we make this connection, this circuit and this circuit, they are equal, and by considering differential mode of operation, we obtained the expression of A d, which is equal to G m, whether it is G m 1 or G m 2, G m multiplied by R c, R c 1 or R c 2, and the common mode gain on the other hand, common mode gain equals to minus R c divided by 2 R t. In fact, to be more precise, this expression it is minus G m into R c divided by 1 plus G m into 2 R t, right. So, the and now we may recall that we want ideally this gain should be as high as possible, and this common mode gain on the other hand, this should be as low as possible. Now, we can see that what are the elements we supposed to be changing. Say for example, to increase this gain, we can replace these two resistors by active device, which may be having equivalent circuit like this, having very high resistance coming from the active device, and that may replace this capital R c by this R naught, and hence that will increase the differential mode gain. On the other hand, if you replace this part by active device having very small conductance or very high resistance, if I call say R t, and by making this R t higher and higher, we can make the corresponding common mode gain lower and lower. So, that makes sense that if you replace these two resistor by active device, and if you replace this tail resistor by active device, performance of the circuit it is getting enhanced. Similar kind of analysis it can be done for the MOSFET version, and the circuit it is very similar. So, you can see the circuit is very similar. So, I am not going to repeat this part, but basically what you can say that you consider two modes of operation, differential mode of operation and common mode of operation, and then you make the connection. From that you can get here also the differential mode gain, it is minus G m into R d, and then common mode gain A c equals to, sorry, it is not minus, based on the definition we are defining the differential mode output. So, this minus is not there, we are considering this is plus and this is minus. On the other hand, the common mode gain it is having a minus sign, G m into R d divided by 1 plus G m into 2 R t, right. And again, to enhance the circuit performance, we like to replace these two resistors, giving us higher differential mode gain, and replacing on the other hand replacing the tail transistor or tail element by active device, that makes this common mode gain going lower and lower. Now, for our analysis we have splitted this resistor, but in actual circuit we will be having only one element. I think most of the things we have covered what we planned. So, the conclusion wise we can say that we started with basic operation of the differential amplifier, rather we started with a recapitulation of basic operation, and also we said that how to characterize a differential amplifier, and particularly how do we get the differential mode gain and common mode gain. And then we talked about realization of differential amplifier using transistor, I should say transistor level realization of differential amplifier. And though the circuit represented circuit, it is I should say simple enough, but that represents most of the cases, and that helps to understand the basic operation of differential amplifier. You also have given a hint of how to get the different variants of different differential amplifier with respect to the basic structure we have discussed. And then we have discussed about the operating principle of the simple differential amplifier, particularly with BJT we have gone in detail how we obtain the expression of differential mode gain intuitively, and also the common mode gain by using the common emitter and common collector operation, common emitter and common collector operation. So, at least we understand that how the basic structure it works, and in the we also obtain the corresponding expression of the differential mode gain and common mode gain through this this analysis and intuition. In the next class, we will be talking about small signal equivalent circuit and arriving the same expression of the differential mode gain and common mode gain using the small signal equivalent circuit of the differential amplifier. I think that is all to cover. Thank you for listening.